Hi, everyone. Welcome back. We're about to kick off Unit 3, which is our Machine Learning Operations, or MLOps unit. All right, so this is Lecture 20, and this is our Introduction to MLOps. So what exactly do we mean by MLOps? This is the standardization and streamlining of our machine learning lifecycle management. So as we move through our machine learning lifecycle, there's different key areas that we can automate, integrate, deploy using some of the cloud native and CI/CD principles that we've already built. So let's talk a little bit more in depth about the machine learning lifecycle and what it is exactly. So machine learning always starts with a research question. So that research question is going to be, what do we actually need to do? What are we trying to predict? What do we need to classify? That's followed by our data collection and our pre-processing. So our data collection could be, collecting signal or traces from our observability pipeline. That could be our external data sets. That could be telemetry it could come from telemetry from IoT devices, whatever that might be. Data collection and pre-processing is a step where you actually amass data into some central location and then do any relevant cleaning or transformations on it that you might need to do. Next up is our experimentation and evaluation. That's where we actually build our model, we do our training and our testing, and then we evaluate those initial metrics. This could also be where your hyperparameter tuning happens. People have been calling that fine tuning these days. Fine tuning and hyperparameter tuning are starting to be used interchangeably, which I guess is okay. Just if I use one term or another, I'm meaning the same thing. After that is model deployment, where you basically take your model and then you plop it into a production system. It has to live somewhere, and then you're also going to determine how often that model is going to be retrained. After that, we have serving and inference. So that's where you actually have some mechanism that can call your model and then generate new predictions or new classifications or do something useful with that model. After that, we have monitoring and maintenance, where we make sure that we check out our model's performance. We make sure we can detect drift, all of those things. So as we move through the AI or ML lifecycle roles, or as we move through the AI or ML lifecycle, there's key roles or disciplines that are going to accompany each stage. So our research question, that's going to be really driven by our domain experts, right? The people who really, they have the problem, they know what kind of task they need to do. Those are going to be business stakeholders or researchers or whoever it might be. And they're going to work with the data scientists to define a research question. After that, data collection and pre-processing. That's going to be a combination of data engineers and data scientists. So those are two different disciplines. Data engineers are going to be more focused on building data pipelines. They're going to be focused on using, for example, dbt to define, model or purpose-driven models for different data transformations, things like that. The experimentation and evaluation stage is really driven by the data scientists, right? That's where we shine. So we are going to build our models, we're going to do our experimentation, keep track of the results, do hyperparameter tuning, all of that. After that, we're going to have our model deployment, and that's where we really persist our model weights or the model object itself. For that, we're going to need to bring in our software engineers and some SREs. After that, we have our model serving and inferencing. So, depending on the type of data or the type of model we have, if we're doing streaming or online data predictions versus batch data predictions, there's going to be some different tools and different, requirements for that. So we're going to really want to make sure we have our software engineers and SREs involved in our model serving and inferencing as well. And then as far as monitoring and maintenance, that's going to be, observability teams and our data science teams. Data science is going to be able to, identify model drift, but observability teams are going to be able to help us, build dashboards, collect metrics and traces about our system overall, and just really make sure that the end-to-end unknown questions can be answered. So there's some key tasks in each stage of our machine learning lifecycle. So there's some key tasks in each stage of the machine learning lifecycle. Let's dig into those now. In our first stage, we're going to define our research questions. Those, again, are going to come from, domain experts, or they're going to be defined by business goals. So some examples of research questions might be, how can we prevent fraudulent actors from onboarding onto our platform or from using our product? Or in the medical domain, how can we better identify cancerous cells from medical imaging scans? Research questions require domain experts because domain experts know what questions to ask, right? So the quality of our questions defines the quality of our lives, and that's really why we want to make sure that we're bringing in the domain experts in order to help define our research questions. Next up, we have our data collection and pre-processing. So this encompasses a couple of parts. So we have data collection and storage. So we're going to find our data sets, collect new data if we need to. We're going to build some ETL pipelines. We're going to identify the appropriate databases and schemas we want to use. And then we have exploratory data analysis. So we've done a bit of this in class before, or you have done a bit of this in class before. And this is where we understand the data set as fully as possible. We do our summary statistics. We're going to identify variables. We're going to identify cardinality and how usable that data is. So how much of that data is actually populated. After that, we have data cleaning. So we're going to convert data types. We're going to impute missing values. We're going to remove outliers if that's required. And then we'll have our feature engineering. So that's where we transform our data to be usable by a machine learning model. We'll do our feature extraction and feature selection. Okay, so data collection and storage. We have different sources for data collection. We can do open source. We can do data repositories. There can be some internal data that we might be collecting. We might be doing some web scraping. And then for ETL, the tools that we want to use are things like pipelines and dbt and Airflow. And for data storage, we can use, databases like, self-managed or cloud-managed databases. We can do data warehouses and even data lakes. For exploratory data analysis, we want to make sure we capture the summary statistics, the number of observations, the number of classes, the number of variables in our data set. And those variables need to also be accompanied by clear definitions. What does this actually mean? What variable is this? How much of this is populated? What's the cardinality? Can we trust the provenance of this data? And then we usually support that through visualizations. So that's going to be things like histograms, scatter plots, and dimensionality reduction. So we'll take high dimensional data, reduce it into 2 dimensions, and then plot that. Data cleaning is a super important step. And we need to make sure that we are, standardizing our data cleaning because we might have to reuse our data cleaning process as we are doing inferencing. As new data is making it to our model, we need to make sure that it doesn't need to go through any other transformations. And if it does need to go through transformations, we need to make sure that we persist the algorithms that we use to do those transformations. So for example, we might want to convert ints into floats. We might want to do some date time normalization. Maybe instead of using the actual date, the timestamp itself, we want to do hours since other event or minutes since some event, that kind of thing. If it's text data, do we want to do case folding? Do we want to do any encoding? Things like that. Imputing missing values, we can impute with a median or a mean or previous value or none. And then when we remove outliers, we need to make sure that we understand our outliers. Are our outliers actually meaningful? Do we want to keep our outliers? Are there any implications for our inferencing stage if we remove outliers or if we keep them? Feature engineering is going to be, a lot of different techniques, as I'm sure you're aware. So with categorical data, we might want to do one-hot encoding or label encoding. With textual data, we might want to create embeddings. For time series data, we might want to remove seasonality from that time series. And then we have our feature extraction. So we'll have some image data where we convert our image data to matrices. We could combine variables, so time since X. We could do some scaling of our features. And then in our feature selection, we want to make sure we're using statistical tests, feature correlation, and variance inflation factor to make sure that our features are legit. So next, let's think about some considerations for our data collection and pre-processing. So for collection and ingestion, there's a lot of different options you can have. So warehouses are very common. So warehouses are going to be some level of standardized data outside of, kind of raw production databases. We'll have our production databases, and those we'll pull data out of and we'll push it into our data warehouse. We'll generally do transformations along the way. There's also data lakes. which are related but a bit different. You'll probably learn about that in your big data class. Obviously, NoSQL databases are becoming much more popular, especially vector databases, given the amount of text data that we're working with. And now EDA. So EDA doesn't necessarily have to be repeated after it's first performed, but it is a critical step before moving on to our cleaning and pre-processing. So all the stuff that we write for EDA, that's really not going to be a part of a pipeline per se, unless your EDA is helping you do some, downstream task. But generally, we'll eyeball the EDA, we'll make our decisions as scientists, and then we'll move forward. So data cleaning. Once we've identified exactly how we need to clean our data, that step can be almost fully automated in most cases. So, once we know, okay, in the warehouse, the timestamps appear like this, we need to make sure that they are UTC or maybe they don't need to be time zone aware, whatever it is that we need to do. Once we have our data cleaning steps, we will probably just fully automate that. And then pre-processing. So pre-processing could be its own microservice because it could be used for both training and also for inference. So we want to be able to reuse that pre-processing function in multiple places. So that's an option for making it its own microservice. If the pre-processing step is going to involve any scaling of features or referring to some dictionary values, like a label encoded dictionary, then you need to make sure that that those values are available at inference as well as at training. So that's another artifact that you might need to persist alongside your model and your model weights. Next, we have experimentation and evaluation. So in our experimentation and evaluation phase, we have a couple of key tasks. First, we're going to select our model, right? So we'll want to identify a model family. Is it going to be clustering? Is it going to be classification? Is it supervised or unsupervised? Then we want to define our model task very clearly. So this supervised classification model is going to do X. It will classify these new data points into fraudulent or not fraudulent. And then we'll make some, key model architecture decisions as a result of the family that we've chosen. Next, we will build our model. So our libraries could include PyTorch, scikit-learn, TensorFlow, and Keras. We need to make sure that we define our input and output dimensions pretty well, especially with deep learning. And then we need to decide if it's going to be a multi-stage model, if it's going to be parallelized, if the training will be parallelized at all, things like that. When we're training, we need to also make sure that we understand our hardware requirements. How much GPU do we need to train this model? How much memory or disk? And then how are we going to persist our model weights and our parameters? Are those going to be written to a local disk to then be read from somewhere else? Are the model weights the kind of thing that you can persist into Redis and then have that read out? Maybe you'll put that into some bucket storage, and then you can pull those artifacts back down for inferencing, all those kinds of decisions. Next, we're going to test and evaluate the model. You need to make sure that you have your evaluation criteria set depending on the actual task that you're achieving. If your task is some kind of ranking task, then you're going to have your ranking metrics. If it's a time series task, you're going to have your time series metrics. The criteria that you evaluate your model on are always going to be dependent on the task that model achieves. Then we want to make sure that we test the model on some unseen data, and then we'll persist those results for benchmarking and for comparison. Once we've done that, then we're going to do some tuning of the model. We will tune hyperparameters or quote unquote fine tune it. And that's going to determine if our model performance can be improved. And if so, how can we improve it? Okay, so here are some key considerations for our model experimentation and evaluation. First, how and where will the model training be conducted? So is that training going to be distributed? Is it going to be localized on one machine? How often will it be retrained? Things like that. What automated pipelines can you use for your model training? Once you've, pushed or merged a pull request into main, does that kick off a new job where the model's trained? Those kinds of things. How will the model training service access the required data? Does that model training service need its own set of credentials so that it can read from your warehouse? Is it going to train exclusively on data that's kept locally? Is it a CSV that gets output that's then local for that model to use for training? How are you going to know exactly what data was trained on and that it was pre-processed correctly? This is where things like data catalogs come into play. So data catalogs are ways of exactly that, cataloging the data that your model trained on. We can also do things like, further attestation of the data that we trained on using hashing functions, hashing algorithms. There's a framework called in toto, so in-toto, and in toto helps you do attribution, I'm sorry, not attribution. In toto helps you do attestation by doing some really clever hashing tricks. So you can hash an entire data set and then provably show that the data that you trained on is actually the data that you've persisted. So experimentation and evaluation. If you're conducting research, which is different than just implementing a machine learning model in production, there's another step in our stage 3, which is benchmarking the model against state-of-the-art models. So evaluation against those models is going to require some additional tests. So for example, you might need to do some students' t-tests to determine p-values for how well your model performed compared to existing state-of-the-art, and just test for statistical significance. And then when we're exploring which features are the most important for our model, we might also want to add features or remove features. And the result of those experiments need to be recorded as well. So recording your experiments and all of the evaluation criteria is a job in and of itself. Next up, we have our model deployment. Sometimes this is called model ops. So in our model deployment, we're going to have a couple of key things. We're going to have our model artifacts. So that's all of our model's assets. So that could be the model itself. That could be the weights of the model. That could be any, kind of sidecar things for our model. So, dictionary encoded values, things like that. Then we have our deployment considerations. How often are we going to retrain? What are our compute requirements? Do we have any sidecars? Are there any audit tables we need to build? Those two things together are going to be our model ops. So that's just really ensuring that the trained model artifacts are persisted, updated, and available for other services and available for observability. So model artifacts can be things like our training checkpoints. Training checkpoints are, as you're training, you progressively serialize the training results to disk. You could also persist those in additional cloud storage. Training checkpoints are great if your model needs to train for like a couple of days. That way, if you lose some work, you don't have to start all the way over. It's a really great thing to look into. Then another model artifact is the train model itself. So we want to potentially serialize that model to disk. We could persist the model in a location that's readable by your inference service. So some cloud storage somewhere, either in either using bucket storage or in a database. And then there's also things like model signing. So signing a model, so showing that the model actually is what you say it is. Then the trained model's hyperparameters, those we can record to an audit table, for example. We want to make sure that we catalog our training data. So creating hashes of our training data and persisting those hashes alongside our model evaluation. Our evaluation metrics, we want to record those to an audit table to make sure that as we retrain, we're having pretty consistent results from training period to training period. And then we also want to make sure that we record our feature importances. Those need to be recorded to our audit table also. This is going to help you understand if a particular feature or another is, overly weighted or underweighted, or if it's being attacked or exploited by attackers, those kinds of things. Then we have our deployment considerations. So what automated pipelines are we going to use for our model deployment? How often is our model going to be retrained? What are the compute requirements for retraining? So are we doing incremental training? Are we doing fine tuning? And what are we going to do about data persistence? So again, those encoded dictionaries or data enrichment or any caching we want to do. Will the training service need to have other persistence requirements? If so, we can use things called sidecars. Those are just going to be, little functions, little containers that write alongside your model training. And then we can also have temporary data stores between model training runs. All right, so some key MLOps considerations when we're doing our model deployment are going to be the availability of our data structures and model artifacts that are created during training, persisting a record of our training data, Securely reading and writing our trained model. So can we write to disk? Is that a safe action to take? When we're reading in our trained model, are we using pickle files, things like that? We need to think about our hardware requirements for training. We need to think about if sidecars are required, and if so, are they allowed in our cluster if we're training on Kubernetes? Container resource constraints might need to be disabled, and there's going to be so many audit tables. There'll be an audit table for your model version, for your model evaluation results, for feature importances, for your data cataloging, and then also for signing your model. So next is model serving and inference. So there's going to be different considerations if you're doing streaming or batch or one-off. Okay, so let's start with streaming. With streaming data, pre-processing needs to be minimal or extremely lightweight, right? So streaming data is, kind of doing online inference. So, of all of these incoming phone calls or text messages, which ones are spam, right? How do we block that? So the pre-processing has to be very, very lightweight. For our architecture, we might need to use something like Kafka that can handle this streaming data. Bandwidth and latency need to be considered. For streaming data, bandwidth is often very high, and you need to make sure that your latency is extremely low as it can get, because you're doing kind of real-time, lightning quick inference. Next is scalability. So is your streaming inference system going to require any kind of elasticity? Data retrieval needs to be minimal or none, right? So we need to make sure that everything that model has to make a decision, everything that model needs to make a decision is already available for it. So it's not going back and querying other services as it's trying to classify each individual data point that's streaming into our inference endpoint. And then we have costs. So costs are mostly going to be incurred from the calling service. So whatever service is calling this model. Next, we have batch inferencing. So in batch inferencing, our pre-processing can be kind of whatever we want. So batch inferencing is going to be kind of maybe once an hour, we'll look back at the data points from last hour and we'll make a consideration. Or maybe it's a one-off process, like you're building a model and you're just going to classify a whole bunch of data once. Or maybe it's every day. You want to go through the last day's user registrations and see if any of them seem like they're coordinated. So there's a really low limitations for preprocessing. You can kind of do what you need to do. Your architecture should be pretty can be pretty flexible. So with batch processing, with batch inferencing, I'm sorry, you can build whatever architecture you need because it's going to run, periodically. Maybe that's relatively infrequently too. Your bandwidth can be high because you don't really have that online requirement, and latency is less of a concern. Your bandwidth can be high because because of the amount of data that you're doing inferencing on at any given time. And latency is going to be a little bit less of a concern because, again, this is running at some predetermined time, and it might not be a blocker for any other system. Scalability, your batch inferencing might need to elastically scale, depending on if your batch sizes are dramatically different between individual runs, or maybe you're only doing batch inferencing once every month, in which case, sure, you want to not have some machine that's just sitting there idle for a month. You want to spin up and spin down that resource. You can do pretty extensive data retrieval without much impact, as long as you're not doing data retrieval that's going to, take out your database because you're doing a massive query. And then your costs are going to be a lot more predictable than with streaming or online inferencing because you're going to kind of have a good idea of how much data you're going to be doing inferencing on. And then if you're doing one-off, just like one-off predictions, in that case, for preprocessing, you might not even need to persist your preprocessing algorithms from your model training stage. As far as inference, you just kind of just have to decide what architecture is best going to suit your inference needs. That might just be on one machine. You train a model on one machine, then you do one-off one-off inference on a huge amount of data, call it good. There's a chance that latency is not going to impact the effectiveness of your product. You know, you can think about scalability, you can think about data retrieval and costs. Really, that's just going to depend on the size of this, this one-off model and the one-off data that it's going to be inferencing on. So it's like batch inferencing, except you just kind of do it one time. So key considerations for model serving and inference. Streaming and batch and one-off inference are all going to have different requirements, right? Different architectural requirements, different compute requirements, and different costs. Your inference service needs to be able to pass the same data as the model training service. So you can't really have features or data that is not pre-processed or not engineered go through your inferencing pipeline or your inferencing stage because your model's not going to recognize it, right? It's going to be the wrong data type, or it's going to be out of bounds, whatever that might look like. Your inference service needs to be able to access the same pre-processing and cleaning processes as the training service. So that's another argument for having your pre-processing and cleaning processes their own microservice. And then your endpoint availability is going to be a top concern during inference. So how, if your inferencing endpoint is not highly available, then there's a lot of implications for that, right? So either customers who are using your AI ML service are not going to be able to actually get a result, or if you're doing like some internal AI ML, then your business stakeholders are not going to be able to get a result. We really need to think carefully about bandwidth and latency when we're creating this inference service. And again, our costs can be unpredictable, especially with streaming or online data. We really need to think about our data retrieval needs, and we need to make sure that our model decisions can be recorded to an audit table. So every data point that receives some kind of that our model operates on, that decision is recorded somewhere. All right, next up is monitoring and maintenance. So this is our observability stage. So we need to make sure that we're regularly visiting our metrics that we used in evaluation to determine if our model performance has degraded, right? So if in our initial training, accuracy was 97% and precision is 97% and it's all looking great, but then that accuracy and that precision gradually decline over the course of weeks or months, we need to make sure that we can see that and that we can identify that. Data quality is a big consideration. So we need to make sure that we can identify any failure modes within our data pipelines between both training and production. We need to make sure that we're monitoring for any kind of cardinality shifts in our data, any missing data or data type mismatches out of range. And we need to make sure that those are kind of taken care of before they hit our model, right? If it's hit our model, that's already a failure stage. Our model is not going to be able to make a decision on that data point. So having observability baked in to identify data quality is a really great idea. Then we have explainability. So our feature importances across training and validation and production environments, we need to make sure that we can identify those, we can introspect on those, we can introspect on our model and build confidence in our model. That way we can also continuously improve our model. And as it comes to drift, we want to make sure that we're monitoring for a change in distributions over time, that we can measure our model inputs and outputs and the actuals or the decisions of a model. So that is going to help us understand if our model has grown stale or if there's any data quality issues or any kind of adversarial inputs to our model as well. So our monitoring and maintenance, we need to think about a couple of key things. How are we handling alerting, right? So if something does go wrong, who's going to get that notification? Will it be an SRE? Will it be the data scientist who supports the model? Will it be software developers? And then how are we going to think about security, right? So metrics are not detections. So metrics are going to help us inform our detections. So, can we set up alerting security alerts around, adversarial inputs, for example? And then periodic reevaluation. Again, we want to make sure that we can continuously monitor how well our model is performing and that we can evaluate that performance pretty easily without too much effort or time. Okay, so let's look one more time at the roles behind the AI ML lifecycle. So we talked this through a little bit earlier. We have our domain experts, data engineers, data scientists, software engineers, site reliability engineers, and observability all working together to, implement this AI ML lifecycle. These are the bits that data scientists are trained to do, right? So this seems familiar from our coursework: data collection and pre-processing, experimentation and evaluation, monitoring and maintenance, those kinds of things. And this is what we're actually doing. So data scientists, depending on the organization that you're at, are going to end up doing this kind of end to end. So this is one of the big reasons that I wanted to have MLOps, and the group project structured the way it is, because then you're going to be able to get a sense of what's required to actually implement a model into production. If you're at a much larger organization with a lot more, or if it's a ML AI focused organization, you'll definitely have distinct engineers working on each parts of this, but maybe you're doing ML in a smaller team for a particular business function, you might be the one doing 100% of this. So just getting used to kind of what we're dealing with when we're implementing models in production, I think is going to be great. And then if you're doing product, you're going to be really able to understand all the stakeholders that you need to work with in order to implement a machine learning model. All right, thank you so much. That's the lecture for today, and we'll see you back here on Thursday. Have a great week.